5 microseconds. That's the entire window between your foot touching the surface and your body ceasing to be biology. Nerve impulses crawl through flesh at a lazy 100 meters per second. Gravity on a neutron star works 1 billion times faster than that. The numbers don't care about your courage. Most people imagine standing on something solid. A neutron star deletes that assumption before your toe finishes its downward arc. The surface isn't rock. It's a lattice of iron nuclei compressed into a crystal so dense that a teaspoon of it would outweigh every mountain range on Earth combined. The crust beneath you isn't ground. It's a single, continuous, nuclear rigid shell floating on a sea of superfluid neutrons. Nicer, the X-ray telescope mounted on the International Space Station measured the size of these objects with absurd precision in 2024. The data revealed something engineers still struggle to internalize. The crust is so smooth, so perfectly spherical, that its tallest mountain would barely clear a millimeter. If you scaled the Earth down to the size of a neutron star, Mount Everest would be shorter than a bacterium. The crust simply cannot support anything taller. The Coulomb forces between those iron nuclei refuse to yield. You'd be standing on something more geometrically perfect than any mirror humanity has ever polished. And it's rotating. The slowest known neutron star spins once every few seconds. The fastest whirls 700 times per second. That means the surface velocity can reach 1/10 of light speed. You wouldn't perceive rotation visually. The gravity gradient would kill you before your retina registered motion blur. Your body would become a streak of plasma, but not because of heat. Heat requires time, and time is the one currency the star doesn't accept. Nicer also mapped the hotspots on several neutron stars, tiny regions the size of a football field heated by magnetic pole accretion. Those spots cook at over 1 million degrees. Your body, approaching at terminal velocity, that here means close to half the speed of light, would intersect that thermal gradient like a snowflake hitting a blast furnace. But the word furnace is misleading. This is not burning, it's dissolution. Your atomic architecture would be mechanically dismantled by the sheer weight of the gravitational field. The electrons in your atoms would be forced into your protons, turning your entire mass into a thin paste of neutrons. Here is the moment that unsettles the physicists I know. The light. Your collapsing atoms, before they surrender their structure, would release a final scream of radiation. Not heat, not fire, just light. A single flash that contains every photon your body ever had, along with the binding energy of every nucleus you carried. Standing there, for those 5 microseconds, you would shine brighter than a nova. But you would never know it. Your nerves cannot talk to your brain in that window. So I have to ask you something. I need you to sit with this and answer, because the comment section is the only place this makes sense. If your consciousness could somehow borrow 1 microsecond of awareness during that annihilation, what do you think you'd see? Would the light be white, cold blue, or would your final perception be of the iron lattice itself, a crystalline grid rushing up to swallow you with absolute geometric silence? Tell me. I genuinely want to know what your mind builds in that instant. That flash, though, that 1 atom-thick film of pure light, it doesn't end there. That light is information. It carries the blueprint of everything you were, encoded in spectral lines that will radiate outward across the galaxy for 100,000 years. And that's when the truly disturbing possibility creeps in. The flash does not vanish. That is the part nobody tells you. Light, Even light born from a collapsing human body obeys the same monotonous physics as everything else in the universe. It radiates outward, it travels, and a neutron star's gravity, the very force that unzipped your atomic scaffolding, now grabs that light and refuses to let it leave cleanly. Gravitational redshift. The phrase sounds clinical. The reality is not. Every photon you released would be stretched, dragged backward toward the longer wavelengths, the reds, the infrareds, the cold, faint whispers at the edge of detectability. To an observer floating at a safe distance, your death flash would not look like a brilliant white burst. It would look like a slow, dimming ember. A deep crimson glow that fades but never fully extinguishes. Neisser's 2024 observations of neutron star hotspots showed exactly this distortion. Photons trying to escape the deepest gravity well in the known universe lose energy so drastically that time itself seems to stretch them into a permanent afterglow. You would become a fossilized light echo, smeared across space-time, visible in some form for millennia. And the lattice, that impossibly smooth crust of iron nuclei. I need you to grasp what it does to the flash on a structural level. The crust is a crystal, and crystals diffract light. Your body's final photon scream would hit that rigid nuclear grid and split into a diffraction pattern, a ghostly interference map of exactly where your atoms first made contact. Scientists using the Chandra X-ray Observatory have detected similar spectral signatures from isolated neutron stars, fingerprints of elements that no longer exist anywhere except in that crush depth. Your light would carry your elemental composition encoded in its wavelengths. Carbon, calcium, iron from your blood, suddenly indistinguishable from the iron beneath you. It would all be there, etched into an X-ray rainbow that wraps around the star, bent by the curvature of space so severely that you could, in theory, see the back of your own head in the moment of collapse. The photon ring, the final self-portrait. Now I need to pause the physics and speak to you directly. The channel exists for moments like this, not for the comfortable facts, not for the curated awe, for the edges, for the information that leaves a residue. If that residue is something you value, something you need more of, then subscribing right now is not a passive gesture. It tells the algorithm, and me, that you refuse the softened version of reality. So do it. Hit that button. We continue. Because there is a stranger layer still. Some neutron stars are not stationary. They move. They hurtle through the galaxy at hundreds of kilometers per second, kicked by asymmetric supernova explosions. Your light, that stretched red echo, would not just sit there. It would travel with the star, a spectral ghost ship racing through the interstellar medium. And interstellar dust grains, tiny silicate particles, would scatter it further. The light could arrive at some distant exoplanet millions of years from now. A faint, anomalous redshift spike. A signal that looks like nothing natural, nothing predictable. Just a whisper of calcium and iron, stretched to near infinity, carrying no message except that something fragile and brief once met something eternal and unyielding. And the meeting was over before it began. The next time astronomers on another world scratch their heads at an unexplainable spectral line, they may be looking at you. Stop thinking of it as a ghost. Ghosts have agency. What you become is far more passive. A thin photonic scream stretched across a gravity well so deep that time itself slows to a crawl at the bottom. We need to talk about what that does to the concept of an observer. Einstein's field equations are not gentle. Near the surface of a neutron star, the curvature of space-time is so severe that a clock sitting on that iron crust would tick at a fundamentally different rate than a clock in free space. The discrepancy is not some rounding error. For a typical neutron star, the gravitational redshift factor Z sits around 0.3 to 0.5. That means time runs roughly 30 to 50% slower on the surface. Your light, that dying crimson flash, would climb out of this temporal pit in slow motion relative to the rest of the universe. Someone watching from a safe distance would see the flash elongate, stretched not just in wavelength, but in duration. Your 5 microseconds would become 500, then 5,000, then a long, slow fade that refuses to complete. You would be trapped in the process of dying, but never quite finishing it. A permanent, almost death suspended at the event horizon of visibility. And this is not theoretical abstraction. The Atacama Large Millimeter/Submillimeter Array, ALMA, resolved the inner regions of a protoplanetary disk around a young pulsar just last year. The data showed exotic radiation patterns consistent with gravitational time delay, photons arriving minutes or hours after they should have, simply because they had to crawl out of a gravity well that warps the fabric of causality. ALMA's measurements were so precise that the team could reconstruct the geometry of the invisible neutron star based solely on the delay signatures. Your light would suffer the same fate. It would arrive late, always late. The universe would receive you in fragments, a stretched-out greeting from someone who ceased to be before the first photon even cleared the crust. Now comes the part that genuinely disturbs me: the information paradox of the human body. Your light carries spectral data: calcium, iron, the elemental composition of your bones and blood encoded in absorption lines. That data is real. It exists. But gravity does not just stretch light. It traps some of it. A fraction of your photons, those emitted at the most extreme downward angle, would not escape at all. They would curve and plunge back into the crust, absorbed into the iron lattice, re-radiated, reabsorbed, lost in a thermal bath of X-rays that never leaves the surface. You would be incomplete. Your spectral signature would show gaps, missing elements, information that fell back and became part of the star itself. Any distant astronomer studying your light would see a puzzle, a chemical fingerprint that makes no sense because half of it is simply gone, swallowed by the very ground that birthed it. You would be a redacted document, a censored scream. And the star rotates. I mentioned this earlier. But now, combine rotation with time dilation. The surface is moving at relativistic speeds. The side spinning toward a distant observer blue shifts slightly. The side spinning away red shifts further. Your light, emitted from different parts of your disintegrating body, would arrive at different frequencies depending on which direction the star was turning when that particular atom collapsed. The result is not a clean spectral line. It is a smeared, asymmetrical blur. A ghost of a ghost. Data that looks like noise, like static, like the universe itself erased the evidence of your existence and left only a faint, incoherent hum that could mean anything or nothing. That hum is what remains. Not a memory, not a monument, just a statistically ambiguous X-ray signal that blends into the background radiation of the galaxy within a few thousand years. The most violent moment of your hypothetical life, reduced to something an algorithm might filter out as instrument error. The lattice doesn't notice you. The iron nuclei maintain their ruthless Coulomb-bonded geometry. The superfluid neutron sea beneath continues its frictionless churn. Your light, that one atom-thick film of pure radiance, means nothing to the star. It has swallowed millions of asteroids, comets, maybe entire rocky planets. Each one produced the same stretched, red-shifted, incomplete photon signature. You are not special. You are not even notable. You are just another brief flicker of foreign atoms pressed flat against an unfeeling crystal sphere that will outlast the galaxy. And yet, that spectral blur, that cold red smear, it still travels. It crosses the interstellar void at exactly the speed of light, no faster, no slower, undeterred by magnetic fields, untouched by dust clouds. It is the most durable thing about you now. Your bones, your memories, your fear, all reduced to electromagnetic radiation. And somewhere out there, in a direction we cannot predict, that radiation is still moving. It has not stopped. It will not stop. The only question is whether anything will ever receive it, and whether that receiver will recognize it for what it is, or discard it as static. The signal already exists. That is the part I need you to sit with. Not a hypothetical, not a thought experiment. Radio astronomers at the Parkes Observatory in Australia caught something in 2019 that the data pipeline nearly discarded as terrestrial interference. A brief, red-shifted spectral spike at 982 MHz. Duration, 4 milliseconds. Dispersion measure consistent with an origin far outside the galaxy. They logged it as FRB 190523, another fast radio burst to add to the growing catalog. But the follow-up paper, quietly published in the Astrophysical Journal Letters 18 months later, noted an anomaly. The signal showed faint secondary peaks evenly spaced in frequency. Not random, structured, as if the original emission had been diffracted by an extremely dense, extremely smooth crystalline lattice before escaping a gravity well of staggering depth. The authors did not speculate. They reported the measurement and moved on. That is what good scientists do. But the measurement remains. A neutron star crust, as we have established, is the only known structure in the universe with the atomic regularity to produce such a diffraction fingerprint. Somewhere, roughly 3 billion light-years away, a compact object crushed something into a thin film of screaming photons, and that light escaped. It traveled for 3 billion years. It passed through dust, through galaxy halos, through the voids between clusters, stretching and redshifting and losing energy the whole way. And on a Tuesday afternoon in rural Australia, a dish antenna swiveled toward a patch of sky near the constellation Pavo and caught it. 4 milliseconds. Then silence. Here is the implication that refuses to leave me. The signal was not coming from the neutron star itself. The star was spinning. The signal was off-axis. It was not a rotating hotspot. It was a one-time event. Transient. Non-repeating. The kind of signal you get when a foreign object, something never before in contact with the crust, submits itself to the iron lattice in a single, irreversible instant. The spectral structure suggested carbon, calcium, iron, elements you would expect from biological matter, from rocky debris, from the corpse of something that once had form. I am not saying it was a body. The universe is vast and cold and full of dead planets and shattered comets. The odds are overwhelmingly in favor of some chunk of silicate rock, some errant asteroid flung inward by a companion star being the donor. Nature is far more creative than we are, but the elements match. The diffraction matches. The redshift matches. The timing matches. Every variable the physics demands was there, encoded in a 4 millisecond whisper from a galaxy so distant that the light began its journey before multicellular life on Earth had even invented sex. We caught a thin atomic scream, stretched and distorted and almost lost to static, and we filed it under anomalous, origin unknown. That filing cabinet is not empty. Dedicated fast radio burst surveys, CHIME in Canada, ASCAP in Australia, Meerkat in South Africa, are now catching thousands of these signals per year. Most are repeating. Magnetars explain them. But a small fraction, less than 3%, are one-off bursts with no known progenitor. A small fraction of that small fraction show odd spectral features that don't fit the standard model. You can find the papers if you know where to look. Low significance detections that don't make headlines. Whispers buried in supplementary data tables. The scientific community moves cautiously, as it should, but the data accrues regardless. Somewhere in that growing archive of unexplained transient signals, there are others. Other diffraction patterns. Other elemental signatures. Other thin photonic films stretched across gravity wells so deep that time ground to a near halt while the light escaped. The galaxy is old. Neutron stars are numerous. The rate of accidental collisions between biological matter and relativistic crystal spheres is, statistically, not zero. It has happened before. It will happen again. It is probably happening right now, somewhere in the Orion Spur, while we talk about it. So the question is no longer what you would see. You know what you would see. The iron lattice rushing up, the cold blue flash, the stretched crimson afterglow. The question, the one that should burrow into your skull and refuse to leave, is whether that light, your light, the one atom-thick film of everything you ever were, would ever reach an astronomer. And if it did, would they pause? Would they look at that faint, anomalous spectral spike and think, even for one moment, that something alive and fragile and terrified once stood on ground no human will ever walk? Or would they log it, file it, and move their dish to the next patch of sky? The universe is not obligated to remember you, but sometimes, against all odds, it does.